A baseball player throws a ball at an angle of 45 degrees with the horizontal. If the ball lands 250 feet away, what is the initial speed of the ball? Ignore the height of the player. For this problem, we have a ball being thrown in the air. Let's start with a sketch. We will have the y-axis vertical. We will have the x-axis horizontal. We have a baseball being thrown, and it tells us to ignore the height of the player. So let's choose a coordinate system in which the initial position of our ball at time t equals 0 will be 0. So in other words, let's choose the origin to be the initial position of our ball. We know that the ball is given some initial velocity at a 45-degree angle above the ground. The problem is we do not know the initial speed in which we give the ball. But we do know that since it is at a particular angle above the horizontal, the ball has an initial component of velocity that is parallel to the x-axis and an initial component of velocity that's parallel to the y-axis. Our goal is to find this initial velocity, to find the x component of the initial velocity, and to find the y component of the initial velocity. To help us do this, let's add those to our sketch. So we know the object has a velocity that is initially directed 45 degrees above the horizontal. The x component of velocity is parallel to the x-axis. The y component of velocity is parallel to the y-axis, and it's thrown with an initial angle of theta naught equals 45 degrees above the ground with an initial speed of v naught, which we don't know. But we do know the relationship of the components to the sides of a right triangle. We may find this useful. So the side opposite the angle, the y component of velocity, we could write as v naught sine theta naught. And for the x component, the side adjacent to the angle, we can write as v naught sine of theta naught. Now, we do know that this ball travels 250 feet. And we know in projectile motion, the motion in which the only influence on that object is the force of gravity. And if the gravity is constant, then the object's motion will be parabolic. So at some later point in time, which we'll call t, we'll call this initial position at the origin, t naught equals 0. So at some later moment in time, which we don't know, the object will have traveled 250 feet. Let's see if we have enough information to determine the initial velocity of this object. From the kinematics equations that we derive for an object under the influence of gravity alone, we have that position as a function of time is equal to an initial position along the x-axis plus the product of the x component of velocity times time for the x component of position, and the y component of position is given as an initial position along the y-axis plus the product of the initial y component of velocity and time minus 1/2 the free fall acceleration times time squared for the y component. So we should remind ourselves that the variable g is defined to be 9.8 meters per second squared, or if we're dealing with feet, this would be 32 feet per second squared. We should also write down some of the values we have. We know we are starting at the origin. So x naught is equal to 0 and y naught is equal to 0. We know the ball lands 250 feet away. So x is equal to 250 feet, while since it lands back on the ground, y will be equal to 0 feet. So let's use some of this information to simplify this formula. X naught is 0, y naught is 0. Rewriting this, let's remember that our position vector has components that are functions of time, the x component and the y component. So let's express our position vector in terms of the components. The x component is given as v naught cosine theta naught t, and the y component given as v naught sine theta naught t minus 1/2 gt squared. Let's now look at the velocity function. Velocity is a function of time based off of the kinematics equations we derived for free fall, is equal to v naught cosine theta naught for the x component, because since the acceleration is only vertical, there is no x component of acceleration, which means the x component of velocity is a constant, plus v naught sine theta naught minus gt for the y component of velocity. Now let's look at these components individually. The x component of velocity we see as a constant, and the y component of velocity varies as a function of time. Remember, our goal is to solve for the velocity as a function of time. So in order to solve for the velocity as a function of time, we'll need each of these components. And in order to get these components, we will need to determine the speed, v naught, and the time, t. So let's look at what we have from position. For the components of position, notice we have expressions with speed and time in it. Maybe we could use those expressions. So in looking at these expressions, we know the total distance traveled is 250 feet. We know the final height is 0 feet. So we know these quantities. Let's go ahead and just call d equal to 250 feet. So this means we have d equals v naught cosine theta naught t, And we have for the y component 0 equals v naught sine theta naught t minus 1/2 gt squared. So what do you think we can do with these to solve for v naught and t? Well, we have two equations and two unknowns. Let's take one of the equations, solve for one of the unknowns, and then plug into the other equation. Since we want to find our initial speed v naught, let's take this first equation, solve t in terms of v naught, and plug it into the second equation. So in doing that, we would get t equals d over v naught cosine of theta naught. Now that we know t, let's plug into our second equation. This gives us 0 equals v naught sine theta naught times t, but t is equal to d over v naught cosine of theta naught minus 1/2 g t squared, which is d over v naught cosine theta naught quantity squared. Well, v naught cancels with a v naught out of that first term. So we have 0 equals d tangent of theta minus 1/2 gd squared over v naught squared cosine squared theta naught. So let's isolate our v naught term. We have 1/2 gd squared over v naught squared cosine squared theta naught is equal to d times tangent of theta naught. We could cancel 1d on either side, and let us go ahead and divide both sides by gd. So we have 1 over 2 v naught squared cosine squared theta naught is equal to tangent of theta naught over gd. Let's take the reciprocal of both sides. 2 v naught squared cosine squared theta naught is equal to gd over tangent theta naught. Let's divide both sides by 2 cosine squared theta naught. So the left side we have v naught squared, the right side we have gd times 2 tangent of theta naught cosine squared of theta naught. Well, working with the right side, I see I could probably simplify those trig functions. Tangent of theta naught is equal to sine of theta naught over cosine theta naught. And then we have a cosine squared theta naught. A cosine theta naught cancels with a cosine theta naught. We have on the right-hand side gd over 2 sine theta naught cosine theta naught. Or if you recognize your trig identities, this right-hand side simplifies to just be gd over sine of 2 theta naught. So taking the square root of both sides, we have the speed, and speed is a positive value because speed is the magnitude of velocity. So we are going to take the positive square root of GD over sine of 2 theta naught. So here is the expression for our initial speed. Let's go ahead and do a unit check while we plug in the numbers. So we get, well, g is 32 feet per second squared. The distance is 250 feet divided by the sine of 2 times 45 degrees. And this is all underneath the square root. Well, 2 times 45 degrees is 90 degrees. The sine of 90 degrees is equal to 1. Plugging into my calculator, I get the initial speed is equal to the square root of 8,000 feet squared per second squared. Now the square root of a feet squared per second squared is a feet per second. So to two significant figures, we get the initial speed of that baseball as being 89 feet per second.